Welcome to Kitchen Table Electronics, Lesson 2, Part 3, Installing and Using the PC Oscilloscope to understand pulse width modulation, so finally we can make a computer-controlled voltage source. Oscilloscopes are devices that display graphically time-varying signals. So in the lab you'd see a unit like this that may have a screen in which an electron beam is swept across this way at a certain speed set by a time base here, which tells you the number of milliseconds per division on the screen that the beam is spending, and then displaced up and down at the same time by an amount that depends on this setting here. So for example, 1 volt per division, and then you can see how the voltage changes with time as you watch the trace on the screen. All of this circuitry here is to make sure that the waveform always starts on the screen at the same position, so it doesn't jitter around as you sample it at various random times, but rather always starts at the same point. That's called the trigger. Our Owon oscilloscope looks a little different. Here it is connected via a USB cable into our laptop, and then on the front panel of the Owon we have 2 connectors here. They're called PNC connectors, into which 2 oscilloscope probes can plug. There is a third general purpose connector which can be programmed for input or output from the screen. And then there is here a little calibration tab that has available a signal of 5 volts at 1 kilohertz. The Owon comes with a DVD for installation. If, like me, you don't have a DVD drive, here is the link to download the software online. You'll see it's actually called the VDS, not the VDU, 1022, that's my bad. PC Oscilloscope, when you go to this link, download it, unzip it, and then double click on it to run the setup package. Install in the default location, which in my case is C program files x86 Owon. And once installed, it should run itself and you'll see this screen appear. Now, when I installed from the DVD on someone else's computer, it automatically found the USB driver and installed it, and then just switched over to auto here. If it doesn't do that, or it certainly won't do that if you're like me when you download the software from the web, what I had to do is this thing just sat there saying offline, and when I plugged in my Owon, it stayed offline. So I went to the device manager, and I saw that when I plugged in the Owon, an icon came up for an unknown device. So that clearly was the Owon. If you go to the driver tab on the panel for the unknown device, if you double click on the unknown device, go to the driver tab, select Update Driver, and go to Browse this computer. Then point the driver system to go look in the Owon folder in the program files, and it should then go ahead and install the USB driver. When you've succeeded in doing it, it might require some plugging in and plugging out of the USB and some closing and opening of the Owon program. But once you've done this, this auto will automatically change to syncing and then auto when it detects the Owon oscilloscope plugged in. Here is a look at the probe here connected to channel 1, and then back to the calibration signal here by clipping it onto the little tab that sticks out here. Notice, by the way, there is a switch on these probes. This changes the sensitivity of the probes from ×1 to ×10. You'd use the ×10 if you had a very sensitive circuit where you didn't want to draw any current from it. They come in the ×10 position by default. I click mine over to ×1, but then you have to go into the Owon software and click on the home button here, and then the channel icon, channel 1, turn it on, and make sure it's on ×1. We'll talk about this coupling in a little bit. Now let's take a look at the specifications for this oscilloscope. This comes from the materials provided with the oscilloscope and you will find them online on the blog page, so you can download them from there. You'll have your own copy if you bought your own oscilloscope. What you see, or you can get them online from Owon, of course. What you see is it says it's a 25 megahertz oscilloscope. This means it can display signals up to 25 megahertz, but only just. It does 100 megasamples per second, so your 25 megahertz waveform would have only 4 samples across the whole waveform. But certainly up to a few megahertz, this oscilloscope is good. This input coupling I said we would talk more about. You saw it was switched to DC in the shot on the previous slide. That means that it's showing the signal as it is, any constant DC level plus the time varying component on top. AC coupling is used when you want to reject the DC level and maybe look at a small time varying level on top of that. Ground is useful when you want to calibrate your display and see where the zero of voltage is. So you would click the ground on, see where your trace was, and then let's say go back and click DC and display your waveform again, and then you'd know exactly where it was with respect to ground. This input impedance here is the effective load the scope presents, and you see it's a mega ohm, which is really very large indeed. It's not a pure resistance, there's some capacitance associated with it, and that's why the word impedance is used rather than just resistance. Triggering, in the case of the square wave, we'll trigger from one edge, and you'll see we can trigger from a rising or a falling edge. There are other options here which you can explore as needed. Usually one will leave it in the automatic or normal triggering modes. Single triggering is when you want to look at an event that is not time repeating, but is triggered by some other source. So you can use an input to that multi-purpose pin to trigger the trace and then see what happens. In fact, you can even see what happens before it's triggered, because this digital scope collects signal all the time, and there is a way of setting this up so you can see the signal prior to the trigger event. There are a whole load of automatic measurements that can be made here, and we'll illustrate some of them. And there's even math you can do on the 2 channels, adding them, for example. And then on an individual channel, you can analyze the frequency content using something called a Fourier transform. The maximum voltage you can put into this is 400 volts peak to peak, and you can change the sensitivity from 5 millivolts per division all the way up to 5 volts per division. That's the vertical sensitivity. The horizontal sensitivity goes all the way from 5 nanoseconds per division to 100 seconds per division. So you can look at an enormous range of timescales. The oscilloscope I recommended you buy costs about $20 more than its cheap brethren. What you're paying for is what the I stands for here in this VDS1022I. It is a USB isolator that sits between the oscilloscope and the PC. Let me explain why this is a good idea. Here is your scope probe. It has the probe that connects to the varying signal, and then a ground clip that would connect, for example, to the ground supply on your Arduino. And you measure the potential difference between the two. This ground clip is connected to your oscilloscope, and then in the absence of the isolator would be connected to the ground on your PC, which in turn would be grounded to the line cord connecting it to the wall. And if it's a 2-wire line cord, then there'd be some other sort of stray coupling to ground. Now, the line ground on power outlets is horribly noisy because of all the other things that are connected to the electrical circuits in the house, light switches and so on. Electric motors particularly bad. And so if there's transient noise, which changes the potential of the ground here with respect to the ground here, you will drive currents through your Owon oscilloscope and into your PC. Even worse, if there is a fixed voltage here with respect to the ground here, you will drive current all the time into your PC. And I can assure you that not only will hang up your PC COM port, but could actually wreck your PC. So having this isolator in here is a great way to reduce both noise and to protect your PC, worth every penny of the extra $20. By the way, if you have some circuitry out here, like your Arduino, that you want to isolate, You could indeed put in a USB isolator, and you can buy these for about $100 or so. But you can also isolate your signal out here when it's in analog form using an analog isolator. Remember, there's a chip for everything. One example of this is the ISO 124 from Texas Instruments. All right, let's run our oscilloscope. So here we are connected to that calibration voltage, 5 kilohertz, 5 volts peak to peak, 1 kilohertz frequency. And let's just go through these buttons at the top. If you click A, it sets the device up automatically. The second button is the run play button, and you saw it stop the data acquisition. The end button is single trace. It just acquires one trace and then stops. So we're going to set it up to play. Now let's go to the home button, and we've selected the option at the top, which is channel. We've made sure channel 1 is on, and we changed the coupling from AC to DC. Now notice that this wave is now jumping around, and we'll see how to cure that in just a minute. This is where I said you change the probe gain, so we're playing with that here. But now let's take a look at this jumping around trace. Oh, I see. I think I'm just checking that I'm on the right probe gain here. But let's do something about this trace jumping around. It changed because we changed the coupling from AC to DC. And so this waveform moved from being symmetrical around 0 to jumping up here. It's edge triggered. It's triggered from channel 1. This is the trigger level, which you see was at 0 volts. That worked just fine when you were DC coupled, but the trigger level was down at the bottom of the waveform when you went from AC to DC coupling. And if you saw, I pressed on this voltage here, brought up a slider, and moved the triggering up to in the middle of the waveform. All right, let's just stop for a second. You probably noticed this was jumping around. The dashed red line was the trigger level. I moved it from 0 volts here up to in the middle of the waveform by operating the slider here that appeared when I clicked on the value of voltage for the trigger level. And I think I ended up with it at about 2.8 volts, which is in between 0 and 5 volts, so it was triggered. And then you probably saw as I went from edge triggering on the rising edge to the falling edge, this waveform switched by 1 pulse. Okay, now we're just taking a quick look at the measurement functions here. There is a whole slew of them, which we get to by checking the channel we want to measure, and you can check both, and the quantities we want to measure. So here's the frequency of period. Here's the peak to peak, 5.4 volts. And you see we get all of these displayed on the bottom of the screen when we check the appropriate boxes on the measurement icon. All right. Oh, you notice, by the way, that there is a hold off. This is for doing this delayed triggering that I mentioned to you. So if you were sending a trigger pulse into that multi-purpose pin, which can be programmed from the settings, by the way, on this home panel, then you could look before even the trigger event. Now, I'm going to go over to the time base here and change from 1 millisecond per division up to 50 microseconds per division. And so now you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions at 50 microseconds. That is 500 microseconds for 1 pulse width. Of course, 1 millisecond for the whole frequency repeat. Of course, now I've gone out of triggering again because I've just changed the sensitivity down here by clicking on this red box for channel 1. So I've now gone back and I've moved the trigger level into range where this triggers properly. Please play with your oscilloscope, test all of these things out for yourselves, and get familiar with it. All right, assuming you have done that, so I assume there's a delay before you look at this next slide, so if you haven't done that, stop running this and play with your oscilloscope. We're going to do an experiment. We are going to use the Arduino to generate pulse width modulated output. And as I promised you we wouldn't be writing any C++ code at the beginning of this course, we're going to do it with an example. So we're going to go File, Examples, Analog, and then AnalogInOutSerial. AnalogInOutSerial. We load that sketch. Here it is. There's a comment section that describes what it does. What it does is to take an analog voltage on pin A0 between 0 and the supply voltage of the Arduino, and it converts the resulting 0 to 1023 number into a 0 to 255 number, which then controls the pulse width modulation out of pin 9. All of that is described here. So we check that our board is connected, and then we compile and load the sketch. Here's the circuit we're going to use to look at this to begin with. Here again is our potentiometer. It is connected to A0 on the wiper. So as this goes from 0 to 5 volts, that is connected with A0 and read by the Arduino with that sketch loaded. Pin 9 now is connected through a resistor and an LED to ground. And so whatever voltage appears on pin 9 will make the LED turn on. Here is the schematic circuit, not very complicated, so I'll let you look at the downloaded file if you want to look at this carefully. Let's take a look at what we see when we run the sketch with that circuit. So I'm going to go over and turn that potentiometer connected to the analog input, and as I turn it up, the LED gets brighter, and as I turn it down, the LED gets dimmer and then brighter again. So what's going on? Let's look at what we saw with the scope probe connected to pin 9, the pulse width modulated output. By the way, 6 of the digital pins have little squiggles on them. That means they can be pulse width modulated. So here we go. We start up at 5 volts, and the signal is at plus 5 volts. Then as we turn the voltage down, you'll see that the voltage goes down for an amount of time controlled by the potentiometer until eventually it's all 0. And as we turn it back up again, it goes up for an amount of time that is proportional to that analog input. That is called pulse width modulation. Why did the LED brightness appear to change smoothly? That's because our eyeballs don't work very well. That pulse width modulation is at a frequency of many hundred hertz, and our eyeballs just cannot follow it. So we think the LED is changing brightness smoothly, when in fact it's being turned on and off like that pulse width modulation waveform we just saw on our oscilloscope. How can we make an electronic equivalent of our slow eyeball? Well, there's a component for doing that, and it's called a capacitor. And in particular, we want a large capacitor, so it's called a polarized or electrolytic capacitor. Because it's polarized, it has different colors associated with each side of it. So a white bar and a black bar with a plus sign here, or sometimes a straight bar and a curly bar with a plus sign here. It's very important that you use these the right way round, because they are actually made electrochemically by oxidizing an aluminum film. And if you bias these the wrong way around, you'll deoxidize the film and the capacitor will short, overheat, and blow up. So the negative lead is the one that's marked typically by a gray band with a minus sign on it, and that's the lead for the negative side of the circuit. Here's the lead for the positive side. And what a capacitor does is to store a lot of charge. So 1 microfarad turns out to store a microcoulomb for 1 volt apply. If you put the charge in and out via a resistor, so the flow of charge is slowed, then providing the response of this resistive and capacitive circuit is much slower than the input waveform here. And don't worry, I'm just telling you stuff that you will understand in much more detail later in the course. Then this time varying waveform here, just as it was averaged by our eyeballs, will be averaged by the resistor and the capacitor to give us smoothly changing DC level here. So here's the circuit we used to achieve that. Once again, our potentiometer between plus and minus 5 volts, with the wiper connected to pin A0 on the Arduino. Pin 9, the pulse width modulation, is connected to channel 1 of our oscilloscope, so we can see the pulse width modulation. It goes from there through this 10K resistor and across this capacitor to produce our DC level here. And then, because this would have a high Thevenin equivalent resistance because of this capacitor, we're going to use our op amp to generate a low Thevenin equivalent resistance output, We put this DC voltage now into the inverting input of our op-amp. We have the output and the inverting input connected together. This is the non-inverting input. We hang our scope probe on the output and we supply power to the op-amp just as we did before. Here's the layout of that circuit on our board. Our potentiometer with the wiper connected to pin A0. Pin 9 here coming in through this resistor and this capacitor to ground here. So we have the DC level here on this white wire, which comes along here to the non-inverting input of the op-amp. The inverting input and the output are connected by this wire loop. And here's the output that we're going to look at on channel 2. So here's the circuit. This is my potentiometer plugged into pin A0 here. You'll see the chip here. Notice that it'll cut out on this breadboard. This means the pins are not connected across here. So just as in the fritzing layout you saw on the last slide, you can connect to pins along here and along here. And that's what we've done. And here's the capacitor and here's that resistor. So let's take a look at what we get. All right. Here is the pulse width modulation. I'm turning the potentiometer. Now we have the scope probe on channel 2 connected to the output of the op-amp. And you can see it's a DC level. It's constant and going up and down as we change the pulse width modulation. This is the first time we've used the scope to measure 2 signals at once. We'll be doing that a lot. So we have a programmable voltage source. Fantastic. Keep this breadboard. We will use it as our variable power supply, programmable through the Arduino. We don't want to use the potentiometer. We're going to set the level of the voltage from our computer. In order to do that, we're going to have to learn to program. I promised you we were going to stick to one language, and I think the most important thing to do is the universal language, as I said to you, which is Python. And it turns out to be very easy to program an Arduino in Python and forget altogether about C++. At the end of the course, when we want to make a standalone instrument, we'll come back to C++, and by that time you'll be so comfortable with Python you won't find it confusing. So, our next task, Python programming. Get ready.